Hello, everyone. Welcome to HDFS, Optimization, Stabilization, and Supportability. I'd like to ask you to bear with me a little bit today. We had a minor technical difficulty, so I don't have the slides in front of me. Thankfully, they're behind me. That just means I have to look behind me, so please bear with me. Thanks. First, a little bit about me. My name is Chris Naroth. I am a software engineer at Hortonworks, and I work primarily on HDFS. I'm an Apache Hadoop committer, PMC member, and also an Apache Software Foundation member, so you might see me a little bit in other projects too. My major contributions to HDFS include access control lists, Windows compatibility, and various operability improvements, and today's talk is very much in the category of that last item. Prior to joining Hortonworks, I was a user of Hadoop since 2010. So my background tends to come from experiences a few years back deploying Hadoop, being responsible for ongoing maintenance, and also developing applications, workflows for analytics on top of those Hadoop clusters. One more note, also this was listed as a co-presentation with a teammate of mine, Arpit Agarwal. I apologize, but he could not be here today, but I still want to thank him for his contributions to the content that you'll see today. To motivate this talk, I'd like to talk a little bit about some of my thinking that was happening in the background prior to writing this talk. Something I've observed is it's always been the case that HDFS engineers are often on the front lines of broader Hadoop operations support. And that is because HDFS is typically the foundational storage layer in a lot of Hadoop deployments. There are alternative file systems available too, but still we see mostly HDFS. Therefore, challenges in HDFS have the potential to impact the entire Hadoop ecosystem. And conversely, a misbehaving application, it's something that hits HDFS too hard, that first manifests as something is wrong in HDFS, and now we need to investigate it. I've given talks in the past at prior summits about some analysis we've done on Hadoop support cases and some of the trends that have been revealed. And something that we always consistently conclude is that investment in operability improvements at the HDFS layer is good for everyone. It's good for the whole ecosystem. So today, I'm going to talk about some of the challenges that have come up in the software and the ways that we've improved them. The way I'm addressing this is by pointing out specific Apache Hadoop JIRAs that I consider very important in recent development. Some of them are very small, and one of the things that continues to really impress me about software engineering in general is that very often a very small change has a huge impact. Of course, not to trivialize it, that just means the hard work went into troubleshooting, into debugging, and actually testing the change. But it is an interesting thing to observe in software development. As I crafted the content for this talk, as I started curating JIRAs, a couple themes emerged. One was optimization, identifying bottlenecks and making them faster. Stabilization, preventing unusual circumstances from happening in the first place and harming cluster uptime. And supportability. Even despite all our best efforts, if something does go wrong, how can we more easily make it identifiable and help get to root cause and resolution more quickly? Actually, I'll go back for one more point. I wanted to make sure to thank everyone in the Apache community. The list of JIRAs that you're seeing today, I certainly don't want to present that they were solely my work or even solely the work of my team at Hortonworks. This is really a community effort. And one of the things I really continue to be impressed by is this community of remarkable contributors and the fact that they come from different backgrounds, different companies, different kinds of deployment architectures, and so therefore they identify different problems and fix different things, and overall that makes it a better platform for all of us. The first topic I'd like to bring up is logging, and this is interesting to me because it's not really a Hadoop problem. It's a problem that can happen to any large-scale code base. Every large-scale code base I've worked on has had problems where there was too little logging, so we couldn't figure out what was going on. And also, the exact same code base, too much logging. When logging is too verbose, it's information overload, and it can even go so far as to cause a performance impact. And to some degree, some of the challenges arise from logging APIs. Again, this is not unique to Hadoop, but right now in the Hadoop code base, there are two different logging APIs in usage. There's a lot of commons logging backed by log4j1. There is also a migration underway in various pieces to SLF4j. With the commons logging API, there is a pitfall of possibly executing expensive two-string logic for messages that are meant for debugging only. So in the first code sample there is this hidden string construction cost for the block object that's being logged. And if you forgot to code that if log is debug enabled, then you would pay that cost every time, not only when you have debug logging enabled. The SLF4j API seeks to simplify this because you simply pass the object into SLF4j, and then internally it makes the decision about whether or not to call toString on that based on the logging level. But the bottom line is we still have these pitfalls around forgotten guard logic. Other problems that come up are expensive logging in a tight loop where it may occur hundreds of thousands of times because we're operating at such a large scale. Another problem that comes up is logging while holding a shared resource, such as a mutually exclusive lock, and then other operations are blocked, waiting for logging to get done. So the first thing I'd like to bring up in this category is Hadoop 12318, better logging of LDAP exceptions. And if you squint at this very closely, this is very interesting because the total size of this patch is 3 characters. It's just the passing of the root cause exception along in the construction of this new inner exception. And it looks very innocuous, but because of the lack of that internal exception, it was very difficult to identify the root cause of this authentication failure. This is definitely one of those cases of too little logging and also one of those cases of very small changes having big impacts. And now we'll swing the other way and talk about a case where logging was far too verbose. HDFS 9434 reported a case where recommissioning a data node that contained 500,000 blocks caused a very long pause on the name node. A little bit of background there. We use the word decommissioning to describe the process of gracefully taking a data node offline. And that works by halting new block writes to that data node and then transferring the pre-existing replicas on that data node to other nodes so that it doesn't accidentally cause under-replication. And that's the point where it's then safe to power off, say, if you want to completely decommission that physical node. Recommissioning is the opposite. A node has been down for a while. You're now bringing it back online. What will happen at that point is there are a lot of block replicas on disk for that old node. But in the time that it was down, HDFS chose to heal. It chose to correct the misreplication from having a reduced number of replicas available for those blocks. So it actually moved copies or created new copies of those replicas on other data nodes. Now that this one is coming back, you will probably have, say, 4 replicas live for these blocks instead of 3. So HDFS goes through a process of, again, self-correcting and saying, we don't need to keep around 4, let's delete 1 and get back down to 3. The problem was this condition was triggering a per block logging message that was very expensive, so expensive that it caused this huge delay in the name node. And here, another very simple patch. We just convert that logging to trace level, and the problem goes away. This is something always to be careful about because I mentioned there's that careful balance between too much and too little logging. In this case, the assessment was made that the message is not generally useful, so shifting it over to trace level logging was acceptable. Moving on from logging, I'd like to talk a little bit more about general troubleshooting. And one of the things that we consistently experience, consistently hear from end users is that Kerberos is pretty hard to deploy and understand. And that's because there are many moving parts to a successful, excuse me. There are many moving parts to a successful, correct Kerberos deployment. It depends on configuration of the KDC, DNS entries. There's the configuration files of Hadoop itself. There is the information of the principles that have been defined. The key tabs need to be set up correctly. A lot of moving parts. Management tools like Apache Ambari seek to automate this a lot, and there are very successful tools for doing that. But when something does go wrong, it's not always easy to understand which of these many configuration points could be going wrong. Another theme we've seen emerge is that metrics are generally the first thing we need to look at for diagnosing any problem. And metrics need to, something we've learned is metrics not only need to identify that there is a problem, but they also need to be capable of identifying the source of the problem. So the difference being, is there high RPC call volume to the name node versus who is making very large, very high RPC call volume to the name node. The first issue I'd like to talk about in this area is Hadoop 12426. And this is talking about the theme of Kerberos misconfiguration diagnosis. And this issue introduced a new tool called Kdiag. And Kdiag is a command line utility that you can issue in any Hadoop cluster, and it will diagnose Kerberos problems for you. We've tried to set it up as a catalog of what are all the things about Kerberos that we've had to check in past support cases, and can we do them automatically? Doing them automatically like this, it's stuff that we would have to do anyway step by step, but doing it automatically like this provides something more consistent and more reliable while we're troubleshooting these cases. This includes information like automatically enabling the Java level diagnostics, such as passing along the -D Sun Security KRB5 debug flag. It also prints various environment variables, system properties, Hadoop configuration options. It will actually attempt to do a login and report whether or not login was successful. If a key tab was in use by the process, that's commonly the case for daemon processes, then it will print the principal information that it found in that key tab. It will print the krb5.conf file that was in use in the cluster. And it will also attempt to validate the kinit executable. The kinit executable may be called in the background for ticket renewals. So it can cause a very hard to understand issue if you get, say, 24 hours into execution of a process and then ticket renewal fails. This is something that can help identify that faster. Next up, we have HDFS 6982. This introduced a new feature called NNTop, and its name is inspired by the familiar Linux top utility that can show you a sorted list of what are the heaviest hitting processes on the node. And we often hear that in troubleshooting scenarios, we want to identify trends for HDFS operations. We want to know where load is coming from. And there's always been the HDFS audit log that has always contained a record of each file system operation received at the name node. And there's also always been a lot of name node metrics available that contain raw counts of the operations that are executing. But one thing that has always been kind of difficult is taking that raw information and actually coming up with some root cause analysis around that. Very often we want to identify who is generating a particular set of operations. And that's something that has always taken a lot of ad hoc scripting. I've had to do that many times myself, string together various tricks with grep and awk to get the aggregations that you want. The goal of NNTop is to provide those HDFS operation counts aggregated per operation and also per user within various time windows. I've given a curl command here. This is just the standard JMX URL that we expose on the name node, port 50070 by default. This gets you a JSON output containing all of the name node metrics related to operation counts. The new thing here is a section called top user op counts. And we see a sample of the JSON output there. And what that's telling us is that there was for the delete operation, there was a total of one call, and that one call was issued by the user Chris. This is a very simplified example, of course, from just a little dev cluster I was running myself. In a larger deployment, what we see in cases of, say, a runaway job that is generating much more load than expected, this is something that can identify the user that submitted that job and show that there are an unusually high number of operations coming from that user. And then you can react to that by initially killing the job to recover the cluster and then starting to analyze what's going wrong in that job, why did it generate unexpected load. Next up, HDFS 7182. This was an important bug fix. JMX Metrics were not accessible while the NN was busy with, the name node was busy with certain operations. And most notably, it was when a particular lock was held in the name node. The name node implementation contains a global lock for certain critical mutations that cannot execute concurrently. The great irony of this, unfortunately, was JMX metrics are often queried in response to operational problems. That tends to be a time when you're under high load, and therefore that tends to be a time when you have contention on this lock. And so unfortunately, at a time when you really needed the metrics, they were not accessible. So this patch addressed the problem by acquiring that same metrics data without requiring the lock to be held. I'd like to move on now to a topic of managing RPC load in an HDFS cluster. Something that we have observed is that it is unfortunately too easy to submit a job that runs away and does something like create a bunch of small files, and this overwhelms the load of the name node with a lot of RPC traffic. The RPC servers, the way they work is they accept calls into a single shared queue. Overflowing that queue causes increased latency. Actually, first I should say really any amount of queuing, any amount of wait time sitting in that queue waiting to execute translates to increased latency for those client calls. If the problem gets bad enough, it turns into an overflow of the queue. And at that point, the server can really do nothing more than just reject the call outright, and that translates to a failure at the client side. Some of these load problems we've discovered can be mitigated with enhancements to admission control, client-side backoff, and different throttling policies. First up in that category, we have Hadoop 10282. This introduced a new feature called the fair call queue. First, a little more background on the Hadoop internal RPC architecture. Traditionally, the way Hadoop RPC works is it admits incoming RPC calls from clients into a single shared queue. There are then a set of worker threads that consume those incoming calls from that shared queue, process them. And in an overloaded situation, what happens is, as I described earlier, we have calls spending more time waiting in the queue for a worker thread to become available. And at the extreme, we have to reject calls because we've run out of room even in that queue. One of the problems with this scheme is that it has a tendency to punish everyone. So if a single runaway job overwhelms RPC load, that there is no room left for anyone in that single shared queue. So therefore, no one can make progress. Hadoop 10282 introduced RPC congestion control using this new feature called the fair call queue. It replaces that single shared queue with multiple prioritized queues. And when a call comes in, it gets placed into a queue matching a priority selection. That priority is chosen based on what is the user making the incoming call and an examination of recent history of that caller's RPC patterns. Calls get dequeued and processed with greater frequency from the high priority queues versus the low priority queues. Now, the effect of this under normal operations, really there should be no queuing at all, and things are just getting processed immediately, and the server is keeping up with load. In that case, fair call queue really has no different observable behavior. It just keeps working that way. Under extremely high load, though, this has a tendency to deprioritize the users that are triggering unusually high load. And that allows room for other processes, other users to make progress. And overall, what this creates is it's less risky for a single runaway overloading job to impact operations for an entire cluster. Building on that is Hadoop 10597. And this added a feature whereby the RPC server could actually signal to the client that it needed to back off because we are currently overloaded. This is very much like the HTTP code that says, please go away for a little while. I'm overloaded. Try again later. The way this works is if the RPC server's queue is full, then the server sends this signal. The client side is aware of this signal and catches it and responds by doing an exponential backoff before sending additional calls. And this is beneficial because it improves quality of service for clients when the server is under heavy load. The reason for that is that RPC calls that would have been rejected outright because the queue is full now are more likely to succeed, just with increased latency. The backoff will trigger, the client waits, the client retries, and it's much more likely that the operation will succeed at that time. It also improves the likelihood of the server recovering because the client backoff will give it more opportunity to catch up with the existing messages in the queue. And finally in this category, this one is very new. I meant to mention what you're seeing today is patches that are in various states of still being written. Some have shipped, some are done but not yet shipped. This one is very recent, allowing more flexibility in those backoff policies. So this is motivated by the observation that triggering backoff when the queue is already full is in some sense already too late. There's already a problem that has grown too big. So instead, something we could do is track call response times, keeping in mind that any amount of queuing translates to some amount of increased latency for client operations. If that kind of key performance indicator goes over a threshold, we can choose to trigger backoff based on that instead of waiting for the queue to be completely full. Okay, the last set of issues I talked about dealt with the issue of how can HDFS better react to an overloaded situation. And now I'd like to shift focus to how can HDFS improve its performance so that therefore it can handle more load, and therefore an overloaded situation is simply much less likely. And on that topic, something that comes up a lot is garbage collection churn. And this has always been a challenge for the name node, where it has a requirement for a large heap, scaling in relation to the number of file system objects in the cluster, whether that means files or directories or blocks or other metadata objects such as snapshots. They all impact the memory footprint of the name node. Something relatively new is that recent hardware trends are also pushing the heap size on the data node. Some fairly traditional advice we've given is that you probably won't need a data node heap larger than 4 gigabytes. That's, I would say, still generally true for most of the deployments I'm seeing. But recently, I saw a deployment that was using pretty unique physical architecture with many drives attached to many fewer nodes. The result of that being that each individual data node is wider, containing many more blocks, and therefore that data node process has a larger memory footprint to track the state of those blocks. And in that case, we had to go all the way to 16 gigabytes for the heap of that data node. So that's a new trend. We've always had recommendations about best practices for garbage collection tuning on the HDFS daemons. But something else we can also do is optimize the code base so that there is a smaller memory footprint for certain critical operations, and therefore there is a reduced chance of garbage collection churn. And one area where this particularly comes up is block reporting. Block reporting is the process by which a data node tells a name node what are the blocks that I hold right now. This comes in two flavors. There is the full block report, which is a complete catalog of all the node's blocks. This is sent relatively infrequently. There's also the incremental block report, and this is partial information about particular events that occurred recently, such as addition or deletion of blocks. This is something that can be sent relatively more frequently, And the idea behind the incremental block report is that clients have some expectation of timely updates of state as tracked by the data node. All block reporting is asynchronous of any user-facing operations. So in general, you don't need to worry about client operations accumulating latency related to block reporting. But something we have observed is that inefficiencies in block reporting can overwhelm the cluster to the point that it's not able to effectively service client operations anyway. So the first thing I'd like to talk about in this category is HDFS 7097, which allowed block reports to be processed while checkpointing on the standby name node. Unfortunately, there was a case where the standby name node generates checkpoints, new FS images, new copies of the complete file system state. That can take a long time to do in a large cluster, and it does need to hold that global lock that I talked about earlier. So while that is happening, there was a problem where we could not process block reports on that standby node. And unfortunately, this could lead to a cascading failure and downtime. While checkpointing holds the lock, incremental block reports are coming in, but they need to acquire the lock too. They can't, so they just sit there waiting in the RPC handler thread. In the extreme case, this can block delivery of an HA name node failover message because that is also RPC. And so if there is no worker thread available because they're all sitting waiting for this lock, then the HA transition can't happen as quickly as we would like. Even if that doesn't happen, an HA failover still might leave the cluster in an undesirable state because if heartbeat processing is delayed, then that appears to the name node like a bunch of data nodes are dead. And so you could have a cluster go through an HA transition and not really be fully functional. So this was an important bug fix. It moved the block report processing so that it could happen concurrently with checkpointing. Of course, multi-threading and locking logic, it's always very scary, so that took a certain amount of reasoning through to make sure that it was a safe change free of data races. HDFS 7435 talks about the way we encode block reports. And the problem was that the way this was encoded had a tendency to be inefficient on memory and generate garbage collection churn. HDFS RPC, like most Hadoop RPC, uses Google's protocol buffers library for serialization and deserialization of the messages. The block IDs and also some additional information about the blocks. This was all encoded as a repeating field of longs, of 64-bit integers. What was not clear until we dug into it was that behind the scenes, protocol buffers would change this into an array list with a low default capacity. That caused a tendency for a lot of reallocation of this array list as it grew to hold many more blocks. And also, there was a lot of cost related to boxing and unboxing because it had to hold capital L reference type long instead of primitive type lowercase long. The solution to this was to take over the serialization within that protocol buffer's message so that we could handle serialization directly and avoid those costs. And we do that by storing directly the number of longs to follow and then deserializing exactly that number of longs. HDFS 7609, avoid retry cache collision when standby name node is loading edits. The background on this is that idempotence and at-most once delivery of HDFS RPC messages is desirable. Idempotence meaning repeated applications of the same operation yield the same final result. An example of that would be something like set permission. You could call that multiple times, and the end result is the same. Those permissions are what you've got on that file. Other messages are not inherently idempotent. An example of that would be something like a rename, because once the rename executes once, the source folder is gone. So it's supposed to reply with a file not found error at that point. But even for things that are not naturally idempotent, we can provide at-most once processing. And the way we do that is we have this data structure called the retry cache that essentially remembers recent operations so that it can remember, OK, this already happened. We can return the same response. And this is important in failure scenarios, such as network partitions or HA failovers, where a client may observe a failure and need to retry the operation, but it doesn't really know what happened on the server side. It doesn't know if the message was delivered by the network, whether it was successfully processed. Unfortunately, there was an inefficiency here that caused collisions, multiple attempts to put the same entry into the retry cache. That storing multiple entries is not something that really made sense, so the data structure does not implement an efficient way to find duplicates and evict duplicates. So this bug fix fixed it at the source. It prevented duplicate entries from being attempted in the first place, and that greatly improved the performance. HDFS 9710 changed the block receipt incremental block reports so that they could be sent in batches. Before this code change, individual block receipts would translate to individual RPC messages, and this would increase overall RPC overhead by sending a ton of messages. The change here is to encode multiple block receipt messages into a single RPC message, and this ultimately scales better with respect to the number of nodes in a cluster and the number of blocks held per node in a cluster, because it doesn't correspond to a one-for-one increase in RPC message load. And now I'd like to move on to the topic of what I call liveness. I lifted a quote here from Wikipedia that it refers to, in a distributed system, the ability to concurrently execute multiple components, even though they have to take turns in critical sections. And what we started to see was that there were problems with data node heartbeats not being delivered in a timely fashion. This could, the failure of heartbeat processing, that can be costly because if it goes on too long, it can trigger a lot of re-replication activity because the name node thinks that node is dead, and now it needs to copy around a bunch of data to restore the replication factor. And this ultimately can cause a cascading failure and lead to downtime. And inspired by that, we came up with this idea of HDFS 9239, the data node lifeline protocol. The idea is to offload whether or not a data node is alive to a separate RPC protocol that would not have to contend on the same resources as mainline HDFS operations, like this shared lock that I've mentioned. And with this in place, even if the main name node RPC queue is overwhelmed, the lifeline can still keep that data node alive. It does so by running a separate dedicated RPC server within the name node to process those messages. And this can prevent that erroneous and costly re-replication activity I talked about. Also related to this, we have the option to offload the HA-related RPC messages to this same server. I mentioned earlier the case of an HA failover message being blocked because of everyone else being, all the handler threads being blocked waiting for that lock. This is something that would have prevented that kind of problem by allowing HA failover to proceed using the separate lifeline RPC server. So at this point, we've talked about reacting better to overload, improving performance to handle more load. And now I'd like to ask the question, where is this load coming from? Is that load legitimate or not? And in many cases, yes, it is. It's just a matter of applications, data sets getting bigger all the time. And so therefore, there is more work for the file system to do. But in some cases, we've observed that applications themselves running on HDFS are not implemented in an optimal way. And I don't say that to point a finger at applications or anything, because to some degree, the file system API, this is the class that interfaces with HDFS from applications. Some aspects of this API, unfortunately, make it too easy to do things that are inefficient. So the first in that vein is Hive 10223, consolidate several redundant file system API calls. In the first code sample there, this is a greatly simplified version of the patch, but there are these calls, file system is file, and then file system is directory. Unfortunately, as simple as that reads, this translates to 2 distinct RPC calls. They're actually just convenience wrappers over an RPC call called getFileStatus. So an optimization we can do here is simply call getFileStatus once and then refer to its results locally more than once. And this doesn't look like much, but the nice thing about this is if you think about it in the context of operating an entire cluster running many Hive jobs, this starts to add up. So this becomes something that's good for Hive because it reduces latency associated with having to make those multiple name node RPC calls. And it's also good for the whole ecosystem because reducing load on the name node is good for everybody. It's a shared service. In a similar vein, we had PIG 4442. And if you look at the before and after, once again, I've spelled out in the comments that this is a case where we had 2 RPC calls really doing the same thing in a row and then just pulling different bits of the response out. And once again, we refactor that into a single getFileStatus call and pull out the properties we need. This one is something that was revealed by manual inspection of the HDFS audit log. And that continues to be a really great source of information for understanding what kind of activity is hitting HDFS. If you haven't already done so, I do encourage you to look at that in your clusters and see if you can identify any interesting trends there for your own workflows. And thinking ahead to some more feature enhancements to the API is HDFS 9924. The current file system API is inherently synchronous. The forward user-facing API calls translate to HDFS RPC calls, and they must block waiting for those responses to come back before they can proceed doing anything else. HDFS 9924 seeks to provide an asynchronous version of that API. And we think this would be very helpful for certain application usage patterns, particularly where the results of operations do not impact the success or failure of subsequent calls. And a good example of this is Hive's partitioning logic, which has a tendency to need to send a lot of rename operations. And all of those rename operations are isolated. They don't depend on one another. So with an asynchronous API, Hive would be able to fan out and send multiple of those calls concurrently and then not block until the end when it needs to get back all of those results. So to summarize, today I talked about a variety of recent enhancements that have gone into Apache Hadoop to improve the ability of HDFS to serve as the foundational storage layer for the Hadoop ecosystem. I saw that they fell into categories of optimization, whether that meant performance of HDFS itself or optimizing the applications. We talked about stabilization, this concept of liveness of data nodes, managing RPC load, and supportability. If something goes wrong, how can we identify it through better logging and better troubleshooting tools? And thank you very much. At this point, I'd like to open it up for Q&A in any of the remaining time. Over here? Are you passing a mic around? No. Go ahead.
Are these patches in 2.7.2?
You know, I'm hesitant to announce our particular patches in particular versions. I don't trust my head for that. These patches are in a variety of states of already shipped or still being code reviewed. I would say the source of truth on all of these is to go back to the JIRA numbers themselves. I can make the slide deck available, and then if there are particular patches you're interested in, you can match it up that way. Or ask your vendor if you use a vendor.
So we run a pretty large cluster, and we hit many of these issues that we saw, yeah, they were already fixed and got it backwards. And I wonder, is there a way of following these improvements without reading all the JIRAs so that I could see this is potentially an issue before we hit it?
That's an interesting idea. Maybe one of the things I'll take back is there are various features in JIRA that could be used to do this. We could, for example, use a performance tag or something. And that would allow you to track the performance tag for new features filed in JIRA and then correlate, does my cluster version have this patch or not? So yeah, thank you for that feedback. I'll think about that, see if we can come up with a good scheme in JIRA to do that. Anyone else I'm missing? Great, well, thank you. If you have any other questions, feel free to talk to me afterwards, too.